Hi, everyone. Today, I would like to talk about what changed for QA when we moved from traditional software to AI systems. This is a not deep technical ML session. It's just QA-focused talk about how logic of testing changed when system behavior is shaped not only by code, but also by data and models. And before we start, let me briefly introduce myself. My name is Daria. I'm senior QA engineer with more than 10 years of experience in software testing across different domains, including finance, CRM, logistics, education, and AI-related systems. I choose this topic because AI features are no longer something exotic. They're already part of real products, and means QA engineers increasingly need to understand not only what AI is, but what it changed in testing. And let me show you what exactly we are going to explore today. This talk built around 5 steps. First of all, we will look at the difference between conventional software and AI systems from the life cycle perspective. We will see what new testing challenges this creates. Also, we will talk about metrics, because in AI systems, exact expected results are often not enough. Fourth, we will look at several testing strategies that are especially useful for AI systems. And finally, we will summarize what all this changed for QA in practice. And to understand what changed in testing, we first need to understand what changed in the system itself. So let's start with the life cycles. This life cycle is familiar to all of us. In traditional system, we usually move through a relatively understandable structure: requirements, design, implementation, testing, deployment, and maintenance. Of course, in real life, this process is not always perfectly linear, but the key point is that expected behavior is usually defined in requirements and implemented in code. That gives QA a strong and fairly stable test basis. In this model, testing is mainly about verifying that the system behaves according to the logic that was explicitly designed and implemented. And let's compare this with the workflow of ML-based systems, because this is the first big shift appears. Machine learning workflow is different from conventional SDLC because system behavior is shaped not only by code, but also data, the selected algorithm, model settings, and the way the model is trained. The first step is to understand that objectives are defined acceptance criteria. In ML systems, these often include performance metrics. From there, we select the framework and build the algorithm. In parallel, we prepare and test the data. And this is an important point. Data is not just collected. It has to be cleaned, validated, and tested, because defects in data becomes defect in model behavior. After that, the models go through training, evaluation, and tuning, like here. I'm sorry. This is a model generation loop you can see in the center of the diagram. Here. This part is iterative. We typically don't know in advance how many cycles we'll need before the model reaches acceptable quality. Once acceptable model is generated, it is tested on independent test dataset. This is different from evaluation during tuning. The test data sets gives a more realistic picture of how the model performs on data it has never seen before. Deployment is not just shipping by the model, it's usually integrated its data pipeline into a larger system. And after deployment, you can see on the right side of the diagram, the model is used, monitored, and tuned over time. Quality work does not stop at release. So for us, the main shift is this. Testing is not limited to the final product. We need to think about data, model behavior, deployment, and governing monitors as part of the quality picture. But the workflow is only part of the story. The more fundamental question: what makes AI system harder to test in the first place? On the slide, you can see 6 challenges. I would like to walk through them not in the order they appear visually, but in the way it shows how they connect to each other. And first of all, this is a complexity. In traditional systems, logic is usually explicit, written line by line. In AI systems, behavior is generated by the model based on learned patterns, and it may be very difficult to trace brick by brick. This directly leads to the second challenge, a lack of transparency. Sometimes we can see the output, but we cannot clearly understand how the system arrived at it. This is often called the black box problem, and it's matter for testing because if we cannot explain a result, it's much harder to define what a correct result should look like. Third, there are robustness issues. Small input change, sometimes imperceptible to human, may cause major output changes. The model may fail confidently on outputs that look completely normal. Fourth, this is autonomy. Some AI systems make decisions with limited or delayed human control, which raises the stakes for getting testing right. Fifth, there are drift both in data and in meaning. The world changes, but the model does not update automatically. We will look at this more closely in dedicated slide. And sixth, there are probabilistic and non-deterministic behavior. The same input does not always guarantee the same output. All of these are important, but I would like to focus more closely on challenges that most directly change testing logic. And the first one is non-determinism. In traditional testing, the logic is usually simple. We provide input X, we expect output Y. If the result is not Y, the test fails. With AI systems, this model often becomes too simplistic. The same input may produce different wording, different scores, different confidence level, or in some cases, even different outputs depending on context, sampling, or internal variability. This changes testing in several ways. And first of all, we cannot always define one exact expected result. Sometimes we need an acceptance range, a set of evaluation criteria, or an expected relationship between input and output. Next one test run may not be enough. If behavior is variable, we may need repeated executions and statistically meaningful observations. Third, if yesterday's answer is not identical to today's answer, this does not automatically mean regression. The wording may change while the meaning remains the same. And finally, when several AI components are combined in one system, uncertainty accumulates, the predictability decreases even further. So non-determinism matters not by itself, but because it changed the mechanics of testing. But even if the behavior were perfectly stable, one more problem would remain. How do we know which result is actually correct? And this brings us to the test oracle problem. A test oracle is a source we use to determine whether a test result is correct. In conventional systems, this often comes from requirements, business rules, calculations, or clearly defined expected outputs. But in AI systems, this becomes much harder. Sometimes the task is too complex for reliable human judgment. Sometimes correctness is subjective. Sometimes different experts may disagree, and sometimes system behavior evolves over time, so previously valid expectations become outdated. This is critical because traditional testing is built on the compression of expected versus actual. If there is no reliable expected result, testing becomes much harder. Take a medical example. If an AI system analyzes an X-ray and returns a probability of cancer, what is the correct answer? 73%, 81%, or only acceptable critical range? And who decided? So if one fixed expected result is often unavailable, how do we evaluate quality at all? One important answer is metrics. Metrics helps us evaluate AI systems when one exact expected result is not enough. Accuracy is the overall share of correct predictions. It sounds simple and attractive, and it works well when classes are reasonably balanced and only types of errors have similar cost. But accuracy can be misleading. One class dominates the data. For example, imagine a fraud detection model where only 10 transactions of 1,000 actually fraudulent. A model can mark every transaction as legitimate and still achieve 99% accuracy. Technically, the number looks excellent, but the model has detected 0 fraud cases, so in practice it's useless. Precision answers the question, when the model predicts a positive result, how often is it right? This matters when false positives are expensive. For example, in spam filtering, we do not want important emails to be incorrectly marked as spam. The same logic applies to fraud detection. If the system blocks too many legitimate transactions, users may lose trust, support teams get overloaded, and the business may lose real customers. Recall answers a different question. Of all real positive cases, how many did the model actually find? This matters when false negatives are expensive, such as in a decreased screening. In that case, missing a real positive case can be much more dangerous than raising an extra alert. F1 score is a balance between precision and recall. It is especially useful when both types of error matter and the data is imbalanced. For example, in a factory defect detection system, we do not want to let defective parts pass through, but we also do not want to stop production for every tiny scratch. That is not actually critical. So when we choose a matrix, we are not just choosing a formula. We are deciding which type of mistakes is more critical for the specific use case. However, metrics can only show us the model's behavior. They do not explain everything by themselves. If the data is incomplete, biased, mislabeled, or not representative, the metrics can either hide the problem or show us the symptoms without explaining the cause. So next, let's look at the data side of AI testing. In AI systems, data quality is not secondary, it's a fundamental. If the data is incorrect or incomplete, the model will learn from incorrect or incomplete information. If classes are imbalanced, the model may appear accurate simply because it predicts the majority class most of the time. If the same examples are duplicated, repeated patterns become overemphasis, and the model may memorize training data of generalizing. That is one way overfitting can happen. And if the data contains errors, the model can learn those errors and reproduce them consistently. This includes labeling error. If training examples are incorrectly labeled, the model learns the wrong associations. And if the data reflect historical basis, the model will reproduce those biases in its predictions. So one of the most important ideas in AI testing is very simple. Model cannot be better than the data it learns from. And even good data is not enough forever. A model can still become less reliable over time as the reality changes. And this slide picks up exactly when we left off. Drift is one of the clearest examples of how AI expands QA beyond traditional release-based validation. The system may still work technically, the data pipeline may still run, the code may still be correct, but something has changed and the model does not know it yet. There are two distinct types of drift. Data drift happens when the statistical properties of input data change over time. The model is the same, but the data coming in look different from what it was trained on. Spam filter trained in 2021 has never seen the new phishing patterns in the exist today. Concept drift is subtler. Here the input data may look similar, but its meaning has changed. A transaction type was once considered low risk, may now be classified as a high risk due to the regulations. The data hasn't changed, but the correct answer has. Both types can happen gradually, which makes them easier to miss without active monitoring. A forecasting model trained before a major market shift, a recommendation system that no longer reflects current trends, a credit scoring model relying on behavior patterns from the several years ago. So our work does not stop at release. We need to seldom monitor metrics on current data and detect drift before users do. So now we understand the problems. The next question is practical. Why testing strategies can actually help? At this point, we already understand that traditional expected result logic is often not enough for AI systems. So instead of relying on one of universal way of testing, QA often uses several complementary approach. And the first one is a relation-based approach. It is useful when we do not know one exact expected result, but we do know how outputs relate to each other over after a controlled input changes. The second compression-based approach is useful when we compare models, systems, or versions instead of relying on one perfect oracle. And the third, robustness-focused approach. It helps us reveal fragile behavior before users encounter in production. So the slide is not about listing every possible technique. It's about showing three practical directions that help QA work with uncertainty in AI systems. And let's start with the relation-based approach and look at metamorphic testing. Metamorphic testing is especially useful when there is no expected result, but we still know something about how outputs change behave relative to each other. Here, the base input is a short review, fast delivery, item arrived intact. When we reorder the phrases item arrived intact, fast delivery, the meaning stays the same, so the sentiment should stay the same as well. If it doesn't, then the model depends on word or sentences order where it should not. That becomes a robustness defect. So the core idea of metamorphic testing is not compare one output with a fixed oracle, but to change the input according to a rule and check whether the output changed in the expected way. This is one of the strongest response to the oracle problem. Another useful approach is to compare not transformed inputs, but entire systems or model versions. Back-to-back testing means comparing two systems, two models, or on the same input set. Instead of asking, is this output absolutely correct, we ask different question. Is the new version better, worse, or meaningfully different? This is especially useful when we do not have a perfect oracle, but we do have a baseline. For example, we can run the same customer support prompts through the current model and the updated model. Then they compare relevance, consistency, error rate, or safety-related issues. This approach helps detect regressions between versions and supermigration, retraining, or model replacement. And if we want to test not only normal behavior, but also fragility, we move to adversarial testing. Adversarial testing is about deliberately looking for inputs that can mislead the model. Let's take a look at this example. Here, the meaning stays the same. This is fraud, do not send the money. But after a similar change in the punctuation and formatting, the model stopped flagging this message as harmful. That shows as an important weakness. AI models can fail confidently in inputs that look completely normal to a human. Adversarial testing helps us identify such fragile behavior before users do. It is especially important when the model receives uncontrolled user inputs or when the system supports high-stakes decisions. So the basic logic is simple. Valid input, small change, unexpected failure. But adversarial testing is only one example of an AI testing strategy. Not every testing problem is about attacking the model or finding fragile inputs. Sometimes the question is different. We change the model, retrain it, or improve the datasets. And then we need to compare its behavior against the previous version or another baseline. Let's look at one more question and decide which testing approach for this situation. And I want to, can everyone read this and visible? Awesome. I'll give you a moment to read the question and the options first. Give me a sign when you finish, please. Thank you. Here the model sometimes confused the dog with a wolf. The teams adds more images of wolves and dogs to improve the model. So the key question is, how do we verify that the model actually improved after this change? You can answer it, yeah. Of course, yes, you're right. Here we have two versions, of course, of model before additional training and after additional training. So the previous version gives us a baseline, a pseudo-oracle. So, and we compare the updated model against it using the same and comparable input data. So And this is a good point to finish the testing techniques part and move the final takeaways. So, what should we take away from all of this? AI testing is not completely separate world from traditional QA. We still need the same fundamentals: requirement analysis, risk-based thinking, test design, test data, integration testing, exploratory testing, regression testing, and communication with stakeholders. But with AI-based systems, the scope becomes wider. We do not only ask, does the feature match the expected result? We also ask what data created this behavior, which errors are acceptable, and which are dangerous. Can similar inputs produce different outputs? Can small change break the model? Can the system degrade after deployments when the real world changes? So QA is still about quantity, quality, risk, and confidence, but not. We also need to connect product behavior with input data, data pipelines, models, metrics, robustness, drift, and operational change. So for us, the main challenge is to keep the same critical thinking, but apply it to the new test objects. And thank you very much for your attention.